Okay, during this second video, we are going to go over the second slideshow, but I'm going to do a quick run through of how you should access the materials because I'm getting a lot of emails that people are confused. So let's take a look at the work plan together so we can figure out how to do this. So some people are asking me if they should submit their notes. You should not submit your notes. Your notes are not actually due till the 30th. So you don't need to take full-scale notes on this yet. It would be a good use of your time, but to ask you to do a whole slideshow on each concept every day is a lot. Well, I have other people who are way ahead of me and have already finished these notes. So I think it depends on you and your pace and what your level of understanding. So when you're on the work plan, you're going to notice that it says, where is the assignment in the last column? There's a lot of instructions here. Quizzes are timed. Each one is 40 minutes. You have a quiz per day, per slideshow, per section of the study guide. So the first thing I'm going to do is I'm actually going to go to the study guide because the study guide tells me what section I'm on. So I'm going to open this study guide. Okay, the study guide starts with some review. I did do that review in the video, and that was just some basic review on, are you sure you know how to count all the atoms in different formulas? Can you balance equations? These are all necessary things before you move on to the next concept. And then it's some new information from the new slideshow, and that's about chemical formulas. So there's two multiple choice questions here, and then a part 2 question. So that's all there is for day 1. I would make sure that you've gone over day 1 very carefully in the slideshow. Make sure that you have, gone through the whole slideshow. But again, you don't need to take notes on it. You need to get a basic understanding of what's in there and how it's used. On the next day, so the next highlighted section, it says day 2. And it tells you it's a companion for the slideshow converting between grams and moles. So each of these questions is a little bit more intense, but this is predominantly application. So if you have done all the application for each one of these sections, you will have done the entire, you'll have done all the application for your notes already. So I am going to go ahead and do the next section. I haven't gotten to the next day yet. I was going to do it in school yesterday, and then the internet went down all day. So the first quiz and the second quiz are up. This will go up a little bit at a time. I'm going to hopefully finish today. So, all right. So next thing I go on the work plan. This says it is the companion guide for the second slideshow. So I'm going to go to the second slideshow. Now, according to this slideshow, it's about converting between grams and moles. So this slideshow opens up with a discussion about what moles are. So at this point in the video, at probably 5 or 10 minutes in, I'm going to actually do the video for this lecture, which hopefully will help you get through the application section and figure out what you need to understand. So I'm going to stress to you quite a bit that one of the issues that you guys have across the board, this is all my students, is you tend to be generalists. That means that you look at the very big picture, but you have a tendency to make too many things all sound like they're the same thing. What I want you to do, and then what we do in the sciences a lot, is I need you to be real specific. And so you're going to see later in the year even that I'm still saying to you over and over again, these two words do not mean the same thing. These two words do mean the same thing. You need to very specifically know the difference. And you have to really make sure in your notes. So we're going to talk while we're doing this lecture, what needs to be in your notes so that you really understand this. So you should know what grams are by now, but we'll review very quickly. Grams are the unit we use to measure mass. Mass literally is defined as the amount of matter in a sample. Okay, this definition is going to take on a whole new flavor as we do this, because we are now also introducing you to a new unit of measurement. And that new unit of measurement in chemistry is a mole. Okay, now I have a bit of an issue with this. So the word mole is actually short for the German word molecule, and I'll get into how that term came to be used for everybody, but it was coined by a particular German scientist. It was actually spelled in German. It didn't have a C in it in German. But the nickname for it was mole, MOLE. So that's actually the shorthand. That's as short as you can go. But it has taken on new definitions. It has nothing to do with this adorable little animal in this picture. So many schools all over the country will celebrate something called Moles Day. And during that time, teachers will make projects. And in the project, the kids will make little moles like the animal. I don't do that project because that little animal has absolutely nothing to do with this unit of measurement, as adorable as it is. And I mean, it is cute. It is cute, but it's not the same thing. Okay? It has to do with this gentleman right here and some other scientists who were working on this issue for a really long time. But they didn't actually know what they were working on. They discovered an important relationship in nature that allowed them to identify a number, which was then later named after this gentleman with too many names. And this man, we're just going to call him Amadio Avogadro for short, although you can tell he has really a lot of names, like almost as many as Albus Dumbledore, who has no chin and very giant eyes and maybe kind of looks like a mole. He was doing work on gases. So he was an Italian lawyer, and in the 1800s, when he was doing this work, he really got into the papers that were coming out from the scientific field. They were considered physicists, the people who were studying gases at the time, and he really got into it, and he just wanted to stop practicing law and become a physicist. God bless him. So he becomes a physicist. He starts doing his own work, which in the late 1700s and early 1800s, that was pretty much how science was being done. You couldn't really do it unless you had money or some occupation that allowed you to have really access to a lot of information, but also to your own private supplies, because there were no scientists at this time. So I'm telling you that there are these physicists and they're studying gases, but the term scientist is really very loose in this time period. These are people who are using their own education and curiosity and financial means to explore the world of science on their own time. And so Amadio Avogadro did a lot of work on gases. There's a video here that will help you understand this a little bit better. But his work doesn't get recognized until after he's dead. And so he didn't discover Avogadro's number. His work led to the discovery. And so it was named after him after he died. So here's what he figured out. What he actually figured out is that if you have two samples of gas, I need to edit this slideshow because this slide is missing. Let's put that in right now. It's actually printed on this. He had a stamp, like a memorial stamp of this, because his discovery was so important. It's sometimes referred to as Avogadro's law. And that is because it is a relationship in nature. I think I misspell this poor man's name all the time. I do because of my terrible Yonkers accent. It's an O, not an A. I just say it Avogadro because of my terrible Yonkers accent, which makes everything sound like an A. So then I spell it that way because that's how it sounds to me. All right, so Avogadro's law says if you have two samples of a gas, and they are at the same, I'm making grammar edits, sorry, temperature and pressure. And both samples are in containers of the same volume. Even if they are different gases, the two containers will contain the same number of atoms or of particles. I'm going to say particles. And the reason I'm going to say particles is because it means molecules or atoms. So, for example, a 2-liter container of argon and a 2-liter container of oxygen both contain the same number of particles. Okay, so this would contain the same number of argon atoms and oxygen molecules. Okay, so this is a little hard to wrap your head around, but he basically does the preliminary work. What he realizes is there's some kind of relationship between the mass of atoms and how many are present in that mass, how many actual atoms are in that mass. So he lays down the groundwork by making this discovery. But this is not, we're not making this happen, meaning that this number is something we figured out. We figured out over time that the number of atoms is in present in a certain mass is actually 6.02 times 10 to the 23rd. And so this was done. I only bring up Wilhelm Ostwald here because it was him who coined the term molecule in German, and he used it as shorthand for the mass of an actual molecule, and this is much later. But believe it or not, we don't figure out the formula for water. We don't confirm it until really late. So we're still arguing about this. We're still trying to understand this, but we've worked it out. Now, later on, other people pick up this stuff that Avogadro figured out about how many atoms or molecules are in a particular volume of gas. And they look at that relationship and they try to figure out whether or not that's the same for other samples. Like, does it work that way for a solid? Does it work that way for all elements? And they continue to do more experiments to prove how many atoms are in a particular sample size by either volume or by mass. And so that's like at least 3 other heavy hitters. Einstein works on it, believe it or not, even though this is not really his area. And then 2 other people work on it, and one of them gets a Nobel Prize for actually proving that in solids, there's a similar thing going on. Not exactly the same as it is in gases, but it is similar. What this number allows us to do is create a new unit of measurement that allows us to count atoms. So this is really important that you understand that this unit of measurement, a mole, I'm going to tell you how many atoms are in a mole. You may not use that number, but that's what we discovered. Over time, with a lot of work, and apparently you need to have the brain of somebody who could win a Nobel Prize to figure this out, that there's a relationship between the masses of atoms, of samples, and how many atoms are in those samples. So that relationship is defined as that there are 6.02 times 10 to the 23rd atoms in this new unit. This new unit, the mole, is what's known as a counting unit. Counting units are not like other units. Counting units literally count how many of something are in an area, but that doesn't mean that the masses are the same. So, for example, this says there are 12 eggs in a dozen. A dozen is a counting unit, just like a mole. It tells you how many of something there are, but it doesn't give you any other information about them. And so if you think about it for a second, think about what we buy in dozens. If I go to the bakery and buy a dozen bagels, and then I stop at the supermarket and pick up a dozen eggs, I know that in my car I have 12 eggs and 12 bagels. But I know that if I put them on the scale or a balance, 12 bagels and 12 eggs do not have the same mass. I just have the same number of each thing. Okay, so this is really a different type of unit, counting units. We don't use a lot of counting units out in the world. We use dozens quite a bit, and it's particularly for buying things. So that's why it's a really great example for this. So this is how we use moles to determine how many atoms are going into a chemical reaction. And that allows us to predict how much of the product is actually going to be made and how much it should weigh. So moles are a useful unit in terms of keeping track of how much matter is going into a reaction and coming out of a reaction. But it's not a great unit in the lab because, yes, it helps me predict how much of something I'm going to make, but I can't measure using this unit in the lab on a practical level. Um, I can't count the atoms. There's no instrument that allows me to count atoms individually. So you're never going to go into the lab and find like a beaker that says like this is fill the container up to here and this is how many atoms will be in there. What you will be able to use is like for example, if I was working with gases, I could use volume because of Avogadro's law, but more practically in the lab, and you will actually do this, we use mass. And so what I want to explain to you is on a practical level, how do we use these numbers? So that number, I really should rephrase this in the slideshow, is this the number that we settled on because it allows us to create a very useful relationship. But to be honest, we're not really creating it, we discovered it. I think that might be a better way to phrase it. I might need to come back and think about it some more. To be honest, every single time I do one of these lectures, I am continuing to learn with you, right? Like when you're first doing these courses, you have a tendency to, just take on face value what this does or what it means. But to be honest, I would like to understand these people's research a little bit better. But I don't think I have a Nobel Prize winning brain. So I still don't entirely understand how they figured this out. But the relationship holds true. And I don't not buy it because I understand that on a tiny level, when you're looking at what atoms are doing and their behavior, we have noticed things about their behavior that is very consistent. Just like we look at the way the density of a material doesn't change unless we change the temperature, we know that there's something going on inside these samples that's making the atoms stay close to each other in a way that allows you to predict how many of them are in a particular sample size. And so that seems to hold true as we go through the whole periodic table, whether you're dealing with a gas, a solid, a liquid. It's been proven in every type of sample. Einstein did liquids. The guy who won the Nobel Prize did something called X-ray crystallography, which actually also played a role in discovering the structure of DNA. And Avogadro worked with gases. So their work put all together allows us to mass samples in grams in the lab and figure out how many atoms we're using to do a reaction. So let's talk about that relationship and where you're going to get it from. So you're going to need your periodic table for this all the time. If you've accidentally left your periodic table, somebody turned theirs in with their exam, which was interesting. A few people did that by accident. You can literally just Google a periodic table, or you can Google the New York State Regents reference table. You may want to start using the reference table from the new Regents, which is 2025. So when you're Googling, make sure that's the one you're clicking on. That new periodic table has a setup that's a little bit more like this, and it is probably the masses that we're going to be using to do these calculations. I have some issues with this periodic table that they put up because atomic masses are calculated to very high precision, meaning that they have a lot of decimal places, but they used more rounded and summarized masses on the table instead of you guys summarizing them or rounding them while you're working with them. So we have a tendency to round these. Like, so I would round 26.9 to 27. But if you were doing this later in your school career in college, you're not going to do that. You're going to work with the big numbers. All right. So according to Avogadro's discoveries and the discoveries that followed after that, what we have discovered is that if you use this counting unit, if you count 1 mole of atoms, or 6.02 times 10 to the 23rd, which by the way is an enormous number, if you put that number of atoms on a balance, it will weigh, it will have the same mass, I shouldn't say weight, it will have the same mass as each atom's atomic mass. So the mass of one atom is also the same number as the mass of a whole mole of those atoms if you weigh it in grams. Now, this is a little hard to follow because I just went from measuring one atom to measuring a whole mole of atoms. But you need to differentiate between these two things. If I'm talking about the mass of one atom, 26.982 is not measured in grams. It's measured in a special unit, sometimes referred to as Daltons or atomic mass units. And the abbreviation for that is a weird atomic mass units. We're going to get into this a lot more next quarter. It's like a weird little, the symbol's called a mu. And it's like a U, like a weird scripty U. I guess I could do like that. Doesn't really. Okay, and that's an atomic mass unit. That's the symbol. Okay, so if I'm weighing just one atom, if I'm massing just one atom, that single mass is 26.982 atomic mass units because this unit is specifically made for measuring tiny, tiny atoms. If I'm measuring a whole mole of the atoms, I switch the units because I'm not measuring one tiny little atom. I'm measuring bajillions of them. That's not a real number, but this is a really big number. This is, 23 decimal places. It's enormous. You could do a little bit of background research if you would like on how big a number that actually is. But to be honest, it's such a big number that I can't even describe to you what that is in like trillions or mega trillions or something really, really big. Um, it's enormous. I mean, a billion is 9 decimal places. So we're on 23 decimal places. It's over 2 times a billion atoms or in a mole. So according to this discovery that we made, If I were to go into the lab and mass 26.982 grams of aluminum, I would have 6.02 times 10 to the 23rd atoms. That is a mole of those atoms. And so this is the relationship that we're setting up. 1 mole of those atoms has the same mass in grams as the mass on the periodic table. So what do I do with this information? That's a really good question. First thing you're going to do, even in your quiz, is you're going to practice assigning mass to a mole of each element. So a mole of copper atoms will weigh the same as the mass on the periodic table, which is 63.46 grams, 546 grams. So if I massed this much copper, I would have a mole of copper atoms. That is why I can set these two things equal to each other. Okay, this now gives me a conversion factor that allows me to go between grams and moles when I'm working in the lab. So I'm going to use this reaction. Copper 2 chloride reacts with aluminum to produce copper and aluminum chloride. Okay, I want you to practice writing your equations, balancing your equations. So this is the balanced version of that reaction. It's very similar to a reaction we're going to run in the lab. We're going to use copper sulfate though, and that's because it's a little cheaper and easier for me to get. So there will be some side reactions happening when you observe this in the lab, but you're going to do this later in either third or fourth quarter. So when you look at a balanced reaction, these coefficients take on new meaning. So this is what I mean by being able to tell the difference between things that are very subtle. And they are different, but all the relationships overlap with each other. And so it's hard to tell the difference. But you need to tell the difference because when you're problem solving, you need to know exactly what you're using and why you're using it. So when you were talking about individual units, this particular formula is for an ionic substance, so I really can't say molecule here. But if I were dealing with, like, so if I'm using 3 copper chlorides, this is copper 2 chloride, or in this equation, I'm actually counting atoms. And up to now, you've been using the subscripts and the coefficients to count how many atoms are going into the reaction, how many atoms are coming out of the reaction. That is correct. But we're going to layer another relationship on top of that. It is slightly different, this relationship. Believe it or not, these numbers do more than one thing, which is why this particular type of formula writing is so useful. I can pack really a lot of meaning into this one equation because these numbers all mean separate, different things at the same time. So while I could say this is 2 aluminum atoms in this reaction, I can also say I have 2 moles of aluminum atoms going into this reaction. I have 3 moles of copper 2 chloride going into this reaction. I am making 3 moles of copper atoms. So both of those relationships, 3 copper atoms, 3 moles of copper atoms, are there simultaneously. Okay? So it's not that these are 2 different things or they don't always mean the same thing at the same time. They mean different things at the same time. That is really confusing. Sorry. So if you have Avogadro's number, you can convert between the number of atoms and the number of moles of substance that you have. I don't know that you're going to need to be able to do this on the regions, which is why I'm telling you not to memorize Avogadro's number. If you were to come across it in a question cluster, I assume that because you don't have this, they would give you Avogadro's number, but they would still expect you to know what to do with Avogadro's number. So we'll get into that at some point. I haven't been teaching it because it hasn't really shown up on the Regents. What you do need to do is know how to use the relationship between the mass on the periodic table and how many moles that is. Okay, so we're going to call that mass off the periodic table molar mass or gram formula mass. Now, these terms are very close in their definitions. Typically, molar mass is reserved for when you're not using a compound, but to be honest, in college, we use these terms interchangeably. In fact, I didn't never heard the term gram formula mass being used. We use the term molar mass. So you're going to hear me say mostly molar mass. I've gotten into the habit of saying gram formula mass because they tend to use that phrase on the regions, but they mean the same thing. What they mean is that there's a relationship between 1 mole of a substance, an element, or a compound, and the number of atoms, the mass of that whole compound or element. Okay, so if you're working with just a straight up element, you don't need to worry about doing any calculations really. But if you're working with a compound, there is a calculation to determine what that number is. So sorry, the picture in the slideshow is of your old Regents periodic table, but essentially I'm going to take the mass number, and again, that'll be on the periodic table, there'll be a key, and I'm going to make a relationship between that mass number and 1 mole of each element. So this definition is important. For each element on the periodic table, 1 mole of it will have the same mass as its atomic mass in grams. I use the word weigh. All right, so how much will 1 mole of each weigh in grams? So you're going to literally look this up on the periodic table. So get your periodic table. Let's go look at it. I'm going to go get my periodic table. I'll show you how to get it. I am going to go to the regions. So I look at that, I didn't even spell regions correctly. I do that every time it's a typing issue. Okay, I'm going to go ahead and go to the new one. So see, it says down here 2025. The 2011 one, we're phasing it out. So I want you to get used to using this one because it's the one you'll have on the exam. Now, for those of you who maybe don't know your elements that well, you will be relieved to see that the names of the elements are on here. However, one of the reasons I really wanted you to memorize or get very good at practicing is because there's still like a lot of elements. And if you don't know what you're looking for, the process of finding each element and then using its mass to do these calculations is going to be more time consuming than it should be. Okay, you should know where sodium is. You should know the symbol for sodium. Sodium is a group 1 alkali metal. The symbol is Na, not S. So if you're still doing that at this point, I'm going to start getting really annoyed with you. Okay, so let's go to the elements that I was given. So a carbon, according to this table, the mass of carbon, I'm going to make it a little bigger, is 12.01. And so, let's see, you should be able to look up these on the periodic table. So make sure you get your periodic table and then we'll go through it. So 1 mole of carbon will have a mass of 12 grams. 1 mole of chromium, look up the mass on the periodic table. Chromium is Cr, it's a transition metal, top row, 52 grams. 1 mole of copper, 64 grams. Now I am rounding. 1 mole of aluminum, about 27 grams. All right. So I can now use this information. So I just got the information that 1 mole of aluminum has a mass of 27 grams. I used the atomic mass on the periodic table to figure that out. So if I am going to use 2 moles of aluminum in this reaction, and I want to do this reaction in the lab, I might make a decision to make the whole recipe. Okay, this, by the way, makes really a lot. So if this were cookies, I'd be making cookies for like 300 people. So I don't probably want to use that whole amount, but let's pretend I do want to use that whole amount. According to my stoichiometry, so this is what stoichiometry is. It's using mass relationships and equations to do calculations to figure out how you want to do this in the lab. If I have 2 moles of aluminum, how much mass of aluminum will I have to mass in the lab to make sure I actually have 2 moles to do the reaction with? So I'm going to use my molar mass from the periodic table. I'm going to use it as a conversion factor. So if 1 mole equals 27 grams, I can rewrite that as a fractional proportion. And if I want to solve for mass, I really should go back into the slideshow and change weigh into mass. I probably did that because you guys confused the two. So I just gave up and started using the term weigh instead of mass. I want to go from moles to grams. So I'm going to put moles in the bottom of my conversion factor so it cancels. I'm going to put grams on the top of my conversion factor so I can solve for grams. Don't forget the order of this math. This is 2 times 27 divided by 1. Okay, so 2 times 27 divided by 1. And that will get me 54 grams. So if I go into the lab and I mass 54 grams of aluminum, I will have 2 moles to do my reaction with. Now, at some point, if people are skipping around or they're really not paying attention, they're going to start to ask me, how do I know it's 1 mole? Please go back and review the video because that is a relationship that has been defined as something that occurs in nature. If I have 6.02 times 10 to the 23rd atoms, which is how many atoms are in a mole, that is how I can determine that that's the number, that's the mass of that sample as I use the atomic mass on the periodic table. So every single gram formula mass, aka molar mass, is the mass in grams of 1 mole of that substance. You're really going to need to spend some time with that. Make sure you get it down. All right, so here are the stats for molar mass. Here's what you do with this. The units for molar mass, because it's grams over moles, is grams per mole. It's how many grams per every 1 mole of that substance that you have. So make sure you understand how to write that, how to use it, what it really means. If you are doing a conversion, but this molar mass or gram formula mass, they're the same thing, allows you to convert between grams and moles for any element or sample of a compound. Okay, so again, they tend to use the term gram formula mass on the on the regions. This is really the term for if it's a compound, whereas molar mass can apply to anything. I tend to say molar mass because molar mass implies that it is the mass of a mole of something. I like that term better. Gram formula mass seems to be about making sure you get the mass in grams of everything in the formula. They're basically the same thing. All right, so you will need the molar mass for each element in a compound. All right, what happens if you get a compound? Right, so up until now, we use just an element. If you're working with an actual compound, first of all, make sure you know what a compound is. But say you're working with water or copper chloride or aluminum sulfate, that's a compound. There's more than one atom there and they're bonded together in a fixed proportion. So now you're going to need your formula reading skills or writing skills. I could give you the name and ask you to write the formula and then come up with the molar mass. So you need to make sure you know how to read the formula and you're counting your atoms correctly, because if you're not, your formula masses are going to be wrong. Okay. And you're going to make a conversion factor out of this that is the sum of the masses of all the atoms in the compound. So let me show you what I mean. So say I get a question that says, hey, what's the gram formula mass of copper 2 chloride? I first have to write the formula correctly. I have to know that this Roman numeral is the +2 charge on the copper, and then balance that ionic formula and make sure I know that this is 1 copper and 2 chlorines. Because if I write it wrong, if I just write CuCl2, when I add everything up, I'll be wrong. My mass will be wrong because I'll have the wrong number of atoms. So I will tell you right now on the regions, they lay traps for you where they will put those wrong answers in the multiple choice. So just be aware of that. So I take 1 copper atom because that's what the formula says I have, and that's 64 grams per mole. And I have 2 chlorine atoms. Each of those chlorine atoms is 35 grams per mole. I have 2 of them. So in total, all the chlorine in this compound has a mass of 70 grams per mole. I then take that and add it all together for the whole compound. And the mass of 1 mole of this whole compound is 134 grams per mole. Okay. So again, this relationship means that for every 1 mole of this substance I have 134 grams of the substance. Okay, now how do I use this? If I have 3 moles of copper chloride, copper 2 chloride, I'm going to start with that given, and then I'm going to ask, what do I have to try and find here? I'm going to try and go from moles to grams. That is what molar mass does. I'm going to calculate the molar mass for that compound. Very frequently, you're going to find that molar masses are given in Regents questions, and that is to speed up your work. They don't want you to have to stop and calculate the molar mass because it's very time consuming. So make sure you're on high alert that they haven't, if they've already given you the gram formula mass or the molar mass, that you don't spend extra time calculating it because you're wasting time. They probably gave it to you. I'm going to make sure you know how to calculate it because that's a separate question that sometimes comes up. Again, I'm going to put my conversion factor so that moles are in the bottom because in this type of problem, I'm trying to get moles to go away and solve for mass. If I were trying to do the other way around, if I were going from grams to moles, I would flip my conversion factor to make sure I'm solving for the right units. Okay, then I do the math. That's 3 times 134 divided by 1. It's 402 grams. Okay, so do this again for 2 moles of aluminum chloride. Pause the video, see if you're getting it right. You know, when you do finally get your notes done for this, you should make sure that you are you're able to do this alone in your application section and you understand the steps. Okay, so calculate your gram formula mass, start with your given, use that as your conversion, your gram formula mass that you calculated. Make sure you've set up your proportion in a way that will help you solve for the units you want and cancel the unit you're getting rid of. And then multiply your given by the top term and divide by the bottom term. Okay, now I'm going to go through these practice questions very quickly and then I'm going to end the video. This is for a type of compound known as a hydrate. This dot is not multiplication. It is a form of notation that indicates that magnesium sulfate, when left to its own devices, will tend to absorb water. You know that water kind of gets attracted to salt, particularly if you're from somewhere tropical or you travel to tropical places. You might have noticed that they put rice in their salt shakers, and that is because water and salts really get attracted to each other. They're really attracted to each other. That's why salt dissolves in water so easily. So there is a weird phenomena where water will hang out inside of ionic compounds, but not actually bond to the ionic compound. So they sort of get trapped, the water molecules, in the crystal itself because they really like each other. But you won't have so much water that the crystal will dissolve. So you're going to get something called a hydrated crystal, crystals with water locked inside their structure. This is known as a hydrate. Okay, and this will tell you how many water molecules tend to get trapped in the crystal per unit of that ionic compound. So this is an ionic compound thing. Ionic compounds tend to do this. So when you're doing the gram formula mass of this hydrate, even though it is not part of the compound, you are going to include the mass of 7 water molecules in the mass of this hydrate. Okay. All right. Determine the mass of 25 moles of acetylene. This is again, you're going to need to go from moles to mass. To do that, you'll need the gram formula mass of acetylene. So let's do a quick example problem. If at this point you've had enough of me and you think you know what you're doing, you can turn the video off. So I'm just going to run through this very quickly. If I have C2H2, to do a conversion from mass to moles, I need gram formula mass because I need to go from grams to moles. And so that's the only way to do it is with gram formula mass or molar mass because it's a conversion factor that has both units. So I'm going to do a little bit of quick math here to get my molar mass. I have 2 carbons and 2 hydrogens. I go on my periodic table, I look up what the masses of those are. Okay, carbon is about 12 grams. I have 2 of them, so I'm going to go with 24 grams. Hydrogen is very tiny. It only has a mass of 1 gram. I have 2 hydrogens, that's 2 grams. So in total, the mass of acetylene is 26 grams for every 1 mole. So 26 grams per mole means that for every 1 mole, I have 26 grams. Make sure you're slowing down. Read it like that. It's out to yourself. Make sure you understand the full meaning. Make sure you're doing your understanding. You understand the full meaning of these units because that is the key to doing these problems correctly. Okay, so I am going to take my given, which is 25 moles of acetylene, and I want to solve for, according to this, mass, so grams. I'm going to then set up my conversion factor so that 1 mole is on the bottom. The reason I'm going to put that one on the bottom is because I want moles to cancel, because the unit I am looking for is grams. Okay, and I'm going to go ahead and put 26 moles on 26 grams, I'm sorry, on the top because that is the top part of this conversion factor. That will give me 25 times 26, and that will give me the answer. That must be a big number. 25 times 26 is big. All right. Now that's definitely a case where they gave it to you. All right, so there's more practice here for you. You should really do that in your application when you get to it. But for right now, you might want to run through the ones that are in the study guide. And then when you feel like you're getting them correct, go ahead and do your quiz. Okay, now this little handy table is for as we move through all the rest of the slideshows, what do you do with each thing that we have learned about? So this is what each of these terms does. This is what units it has on it, and this is the conversion factor it produces. Now, this is the kind of thing that you should be doing when you're doing your understanding in your application. Why is this demonstrating understanding? I was able to identify what this does and how it's measured. I could show you, get it all summarized in one place. Okay, how is this application? It tells you exactly what conversion factors it produces so that you can do the problems that you need to solve. All right, I'm going to call it here. I hopefully didn't get to go over too much.